So part 3 of section 10.3 on polars is we're going to talk about the area enclosed by polar curves. Let's think for a minute about what we do in rectangulars. If you can look at the figure on the left, you can see that in rectangular coordinates we have our function f of x, and we imagine drawing a rectangle, and we try to describe the area of that rectangle we call delta area. It's base times height of a rectangle, which in our case here is going to be f of x times delta x. So we're going to try to do a similar thing in polars. So if you look at the second figure there, where you have the curve, the polar curve in green, then remember thinking like we do with sweeping through Doppler radar, instead of a delta x, we're going to get a little thin angle here. So that is going to be a delta theta. So the idea is that this little slice of pizza, if you will, or this little piece of a circle is called a sector. Now, the way we do it in general is if we have, imagine that's actually a circle, and if we took a part of that circle and we wanted to know, what's say the area of that piece in here, what we do is we take our angle theta. Now, you can see that pretty easily would be like, we're going to think in radians. So we would think of that area of that, my delta area in this case is going to be that quarter circle. But we would take the angle that we have theta divided by, so in general we're taking theta divided by what the whole circle would be, which in radians is going to be 2 pi, and then we would take that fraction, so that angle that we got, our delta area would be that angle, and then times the area of the whole circle would be pi r squared. So a delta area here we would see is, it's pi over 4 over 2 pi, that's a fourth of a circle, and we would multiply that by pi r squared, the area of the whole circle. So what we are going to do in our case here is we are going to say our delta area is going to be our angle, which is going to be that little delta theta in a moment, divided by 2 pi. So that makes this the fraction of the whole circle that we would get if we extended that, if we thought of that sector as being part of a whole circle, and then times pi r squared. Simplifying that a little bit, we can see that the pi's will cancel, and we're going to get theta over 2 times r squared. And so in our case, that theta is going to be that little delta theta. So because as we did in the case of rectangulars, we're going to let that delta x that we did in our rectangular form go to 0 as we sum those rectangles up to get the area under the curve. We're going to let the delta area go to 0, the delta theta rather, go to 0 as well. So our delta area is going to be pi, let's write it, so our delta area is going to be our delta theta over 2 times r squared, or we will write that as 1/2 r squared delta theta. And then if we think of it more in the symbolism of calculus, that delta area will be the differential area, and we'll think of that as being 1/2 r squared d theta. And remember that r is going to be given to us as some function of theta. So r might be, think like a rose curve or a Limasone or something like that. So we build on it then. And so we're going to then add all those little delta areas up and take the limit as it goes to infinity, and we're going to come up with an integral. So for area in polar coordinates, we're going to think of taking the area of the region, between the origin or pole, either way, between the origin and our curve, which we are going to call r equals f of theta. So think like a Lymasone or a rose curve or something like that. And then we're going to get our boundaries on that are going to be not like we would say just A to B in rectangulars. We're going to suggest angles. So we're going to use these Greek letters for alpha, for theta between alpha and beta. So the alpha and beta are angles. So what we're going to get then is our area is going to be that integral from alpha to beta of, we've got 1/2 r squared d theta. Or if you want to think of it more in terms of that f of theta, we can say from alpha to beta of, and we'll call that f of theta squared d theta. So that's going to be our formula for finding the area in polar coordinates. So let's do a couple of examples. So our first example, we'll say find the area of the region enclosed. So find the area of the region enclosed by the cardioid. So I'm going to give you a cardioid. R is equal to 2 plus 2 cosine theta. So we can graph this by hand. I would encourage you also to graph it on your calculator, because eventually, as is the case most of the time with polar areas, we're going to have to use our calculator to evaluate it anyway. I know that's disappointing for some of you. We're going to choose theta to be, we're going to go from 0 to 2 pi. And you can choose, if you choose your window, and the x goes from -6 to 6, and the y's go from -4 to 4, you'll get a pretty good picture of that cardioid. Now, I would encourage you also to put that little circle on the graph, and because you'll notice that when you do that, and you kind of have to always be careful of this when you're in polars, is notice that it traces the graph exactly once. So the graph is traced exactly once. And we have to be careful of that in polars, because as we saw in the earlier example in the previous video, sometimes it'll trace over the curve more than once, twice sometimes, and then you're not going to get the answer that you need to. So here we go. We're going to say the area is going to be, we can pull that 1/2 out. We're going to have the limits of our integral are going to be 0 to 2 pi. And we are going to take that 2 plus 2 cosine theta and quantity squared d theta. Now, hopefully you've already got that entered into your calculator as R1. And so I think you can, let me see. So since you have the R1 already in your calculator, you can just go second mode to get to the home screen. You're still in parametric mode, so when you do the Math 9 to the numerical integration, you can still do it just exactly as you would have. You can go 0.5 times Math 9, 0 for the lower limit, 2 pi for the upper limit, and when you go to the variables, right arrow, go down to polar, and then when you hit enter, you can hit the R1 squared and go d theta, and it should give you, if you're doing that right, 18.850. And that's our answer. Let's do another example. So let's choose this time. We are going to find the area inside the inner loop of a looped Limassone. So find the area inside the inner loop of the Limassone. given by r equals 2 cosine theta plus 1. We usually write this the other way as 1 plus 2 cosine theta, but still recognize what it is. So you should get, I think, something like, let me see if I can change colors here. So you're going to get something that is going to, I believe, look something like that. So we are trying to find, then, we're trying to find the area of this region in here, that inner loop. So to do that, we need to figure out what are our boundaries, what are our limits going to be on the integral. So we want to know, when does that curve first cross through the pole, and then it's going to be inside here, and then when again is it going to exit there and go out from the interior there. So that's going to happen when our r is equal to 0. That's when it's going to be equal to the pole. That's when it's going to cross through the x-axis. So we have to take our f of theta, the 2 cosine theta plus 1, and set that equal to 0 and solve for that. And we're looking for answers that are going to be between 0 and 2 pi. So we can, as we have not done in a while, but we used to do back in our AP prep days quite regularly, we'll get cosine by itself. And so we are going to think for a minute and say our reference angle, cosine is a half at pi over 3. If we think in terms of where cosine, so at 2 pi over 3, at pi over 3 rather, I'm sorry, at pi over 3 is where that is first going to be 0, and then it's going to also be pi over 3 down here, which would be at 4 pi over 3. So this is going to cross through there. The first time it's going to be 0 is going to be at pi over 3, and then it's going to cross into quadrant 2 and be negative, and it will stay negative all the way through quadrant 3, and then we'll come back out on the other side and be 0 again at 4 pi over 3. So we can then say that our area is going to be, again, 1/2 the integral from, we will go pi over 3 to 4 pi over 3 are going to be the limits. And we're going to take our r squared, which in our case is going to be 2 cosine theta plus 1 quantity squared, and then d theta. We can punch that into our calculator, and hopefully we will agree that it's going to be a 0.544. Okay, so I'm going to stop here in this version, and I'll do one more video with polars before we're finished with that.